Thank you so much. Good morning, good afternoon, good evening, wherever you might be watching live or after the fact. My name is Sinan Ozdemir. I will be presenting to you today for modern AI agents from A to Z, building agentic AI to perform complex tasks. I'm really excited to be here. I have given this talk in various formats. In fact, if you have gotten onto our GitHub already, you should have a link to the GitHub and to the slides. You'll notice that the GitHub is actually branded for my O'Reilly course. This is actually an O'Reilly course that I give. That's usually 5-6 hours long. So we're going to be kind of condensing things down to 2 hours today to talk about how to build agentic AI. Now, I am aware you've been in these lessons all day and all week and all everything. So I want to make a few things clear up front. I'm also getting my slides in order. Great. Well, we're going to start with some basic, what are agents? What is all of that? What are LLMs? We're going to breeze a lot through that because, again, you've been inundated with several people talking about different frameworks, different paradigms like reflection, probably plan and execute, React. And we are going to go through all that. Again, I do intend this to be a really A to Z talk slash workshop. And there are going to be coding segments where, depending on time and number of questions that we get, I might either actually run through a lot of the code, show you a lot of the code, because there's definitely way more code in the GitHub than we are going to have time to walk through step by step. So with that, go ahead and ask questions as we go. I am here in usually sunny, but not today, San Francisco, and hopefully everyone is chatting in from somewhere fun and enjoyable. So, what are agents? Of course, you've heard this definition over and over again. Maybe you've heard different variations of these. Of this definition, but generally speaking, agents are semi-autonomous systems that can perform in environments, make decisions, and ideally can adapt and improve over time. Although that kind of promise is more of a promise these days and not so much of a built-in into most agentic workloads. We've probably heard this already, but the idea that an agent is different from an LLM should be pretty clear by now. Of course, agents are not too much more than LLMs with the ability to call tools and functions, whatever the framework will call it. But at the end of the day, an agent is going to be an application of an LLM with access to some kind of environmental reasoning. Now, one of the first things I like to say in these kinds of agent talks is that you've probably already interacted with an agent in your life before, because ChatGPT itself is an agent by that definition. ChatGPT itself is not an LLM. Now, to be fair, there is an LLM under the hood called ChatGPT, but the fact that you're allowed to change the LLM powering that system and still have that conversation makes it an agent. In fact, we'll actually see ChatGPT as an agent, working as an agent in just a moment. Now, that's a relatively fair assessment of agents versus LLMs, but to break it down even more, agents end up being just simply prompts on top of an LLM with a specific task or goal in mind, with access to certain kinds of tools, and generally given some restrictions around rules, backstories, descriptions. The name of this will vary. So we generally have 4 main components to think about with an agent. The task or goal, which is the thing you want the agent to do, look something up for me, make me an image, go book me a flight to Detroit and back, or whatever it is. Tools, which give the agent the ability to actually do something useful, i.e. go actually look that up, or go actually navigate my computer through something like computer use, which, yes, itself is also a type of agent. Then we have rules, descriptions, and backstories, which is generally, again, the context around the actual task itself, meaning only speak in Spanish, or you are talking to a child, so please revise everything you're going to say to act like you're talking to a child, or whatever that might be. And then the prompt itself, which is the consolidation of all of those things into a set of instructions to an LLM. If we think of an agent with these 4 breakdowns, we can not only start to talk about the frameworks that are already out there, but we can also talk about, which is going to be a pretty big moral of today's story, which is how can we actually work towards building our own agentic frameworks? And this is actually the main goal, pun intended, in a lot of my agent workshops, which is to say, we can replicate a lot of the really basic interactions of agents ourselves. So instead of using a framework, let's say like CrewAI, we can really replicate a lot of that functionality in our own frameworks. So you've seen examples of these, so we don't really have to belabor that point too much, but we can give it a task like go to this website and summarize it for me. A tool might be web scraping, and then you might give it rules like don't forget to check the whole website. And the prompt would be how we actually turn all this into a set of instructions. So I mentioned ChatGPT as an agent, and I stand by that. In fact, it is probably one of the first modern agents that really kicked off this wave of agentic AI. And I mean ChatGPT in some of its earliest days. Now, in its earliest days, ChatGPT could not do things like look up things on the web or draw images for us. But if you ask ChatGPT today, if you ask it, what tools do you have access to help me, it's going to say at least these 4 tools. In fact, if you say today, it might even give you more tools than the 4 I'm listing here. But these are the 4 that you're probably aware of. The fact that ChatGPT can remember things about you, it calls that its bio tool. The fact that it can draw images for you, it does that through a diffusion model called DALL-E. So ChatGPT itself, to draw an image, it has a tool that calls the DALL-E API to do it for it and then shows it to us. Python, it can write and execute Python code within its environment, and web, which is looking stuff up on the internet. Now, like I said, if you ask it today, you might get even more than these 4, but these are the 4 core tools. And again, when we're thinking about agents and ChatGPT as an agent, there's the LLM under the hood, and it has a prompt with access to these tools. Well, what is that prompt? A little bit of prompt injection. Sorry, OpenAI, don't be mad at me. But this is a pretty well-known trick. You can Google ChatGPT's prompt, and you're going to get the answers not just from me. But if you do a little bit of prompt injection into ChatGPT, you can start to see how that prompt organizes the tools into the environment. It'll start by saying things like, you are ChatGPT, a very common way to start most prompts, a large language model trained by OpenAI, blah, blah, blah. You see the knowledge cutoff from when I took the screenshot. And then there's a very clear list for where the tools are. And the fact that it's in bold is most likely because the prompt has markdown within it, which is also why ChatGPT probably really likes to give markdown as an answer. And then you can see here where it says bio, the bio tool allows you to persist information, address your message to equals bio, and write whatever information you want to remember. That's going to be pretty important, because the idea that not only does it have access to tools, but the LLM is also tasked with writing the input to those tools. All of this is part of pretty much any agentic framework. There are other examples besides ChatGPT, of course. I'll point you to one, though, in particular, because it will also prove part of my point. If you've never heard of Thomson Reuters before, well, now you have. Thomson Reuters is a very large company. Some might call it a conglomerate. They do a lot of different things. One of the things that Thomson Reuters does is they created and house a legal database called Westlaw. If you've never heard of Westlaw, ask your lawyer friend. They've definitely heard of Westlaw. And they had announced an agent called CoCounsel. They didn't really call it an agent on their website. They call it a legal AI from Thomson Reuters. But really, as the definition of agent goes, it is an agent. They claim, or not claim, they say that they use GPT-4 under the hood, which is not a problem. I have no problem with that. What makes what makes CoCounsel useful, though, is not the LLM in this case, because they're just using OpenAI. They're not really using any difference in LLMs that you or I might use. The difference, though, is the tool, is the data behind the scenes, the fact that they are using Westlaw as a lookup of information. Now, to be fair, some of you are probably thinking, well, Sinan, that basically makes it a RAG use case, not an agent use case. And to which I would say, you're not technically wrong. I would then come back at you with the argument that says, well, agents are basically RAG plus more tools. The fact that this agent has the ability to look up things in Westlaw, yes, makes it retrieving and augmenting its own generation with it, but an agent is simply A RAG, where the thing you are retrieving might not be from the web or Westlaw, but it might be an image from DALL-E. So any kind of prompt that is allowing the system to reach out to an external system and observe the results, I would argue is an agent. So under that definition, you would say any RAG system is an agent where the only tool at its disposal is the lookup from a vector database, a graph database, wherever it might be. Now, the nuance that would might come in is to say that from early to modern agents, what you're really talking about are rules all the way to semantic kind of logic generation. Early AI agents existed. The fact that you could ask Alexa or Siri to do something for you and it would in fact do it for you, no matter how simple it might be, technically make them agents under a pretty strict definition, or a pretty loose definition, right? If I ask Siri to set me an alarm and it does the actual alarm, that makes it an agent. It's not an LLM, or at least it didn't used to be an LLM, but frankly, that doesn't matter. These rule-based LLMs, or sorry, rule-based agents still were agents. My own company, if you're looking at this Kylie.ai here, Kylie.ai is a company that I founded in 2015, and it went through YC and is regarded as one of the, if not the first generative AI agent company to go through Y Combinator. Mind you, this is 2015, where we're using RNNs, LSTMs, but those RNNs and LSTMs, which were generating conversation, also had the ability to ask an API or a Chrome extension to screen scrape, move the mouse around, click on things, grab information, and send it back to the AI. That is an agent. It wasn't using the transformer because the transformer didn't exist yet, but this whole paradigm has been around for a while. Modern LLM agents are not using rules anymore per se. They're generating their own rules through the LLM's ability to reason and through well-structured prompts. I'm actually seeing a comment already saying, I think the exact same thing about RAG and agents. Now, to be fair, people will probably come back at me and say, well, no, that's not fair because RAG has more rules, blah, blah, blah. Sure. And again, agents are not a textbook definition. Sure, I've written textbooks and I've included definitions of agents in it, but there is not a single unified definition that I would argue everyone agrees to. So if you take the definition that agents are just LLMs with tools added to them, RAGs technically become agents, where the tool is look up something in a vector database. Broadly speaking, when we ask an agent to do something, there's generally 4 steps to that process. When you ask an agent to say, who is that person, or look this up for me, the agent is going to go through 4 steps. At first, it's going to have a thought or a reasoning step where it's going to say, okay, to do this, I need to look this person up on Google or on Bing or on DuckDuckGo or Tvili or Exa or SERP, whatever, name your web lookup engine of choice. Then the agent is going to pick a tool. That's the action phase. It's going to pick one of the tools it has the ability to pick from. One of those tools might be nothing, which is to say, I'm just going to respond to this person. Then the tool is going to come back with an observation. The tool is going to actually execute outside of the agent, and the observation is going to get passed back into the system. And then finally, the 4th step is, I need to respond to this person. Now, if you think about an agent with these 4 steps, that thought can really be referencing any number of items in the tools, in the toolbox, let's call it. So it could be a Google lookup. It could be a stable diffusion call to an API that will actually grab stable diffusion images. It could be your own custom API where you want to maybe do something like Alpaca. Alpaca is a third-party stockbroker and crypto broker API. So if you want to tell it to look up the price of something and buy a certain number of shares, and you hook it up to an Alpaca API, boom, now your agent has the ability to look up stock information and execute on your portfolio for you. So it's really anything that has the basic ability to be called through an API or some kind of synchronous system generally. Now, the part that makes an agent more interesting is the fact that those first 3 steps tend to repeat. The agent will have a thought like, I should look this up. It will pick a tool at the action. It will call that action by also generating the inputs to the tool. The tool will execute and the observations will come back. And then that will repeat. The observation will come back, and then the agent generally has another thought that says, okay, I did this Google search, but I did not get what I wanted. I should do another Google search to yada, yada, yada. And then it will keep repeating this until it decides it's ready to answer the question. And then it moves to the final, fourth and final step, which is the response to the person, to the entity, I should say, who is communicating with that agent. So at this point, we can start to talk about frameworks. I'm not going to bore you with kind of I assume, reiterating a lot of the frameworks that you've already heard of, but I'm going to mention a few of the major ones just to kind of be explicit here. We have LangChain, which is a package full of reproducible Pythonic LLM machine learning components. With the actual agent platform of that would be LangGraph, where you can take tools and components from LangChain and build stateful multi-actor applications with LLMs. A lot of the code on our GitHub are examples of LangGraph. If you are thinking of asking me, I'll answer it right now. What's your favorite AI framework? I don't really have one. Well, that's not true. It's LangGraph. My favorite agent framework is LangGraph, but I don't actually use LangGraph in my day-to-day. What do I use in my day-to-day? I made my own. And I think that's going to be part of our section today as we talk about how do you actually work towards making your own agent framework. In fact, there are code examples of using my own agent framework in our GitHub and then how you would actually make your own. But if I weren't using my own framework, I would genuinely turn to something like LangGraph. As a developer, LangGraph gives me the most control over the workflow of the agent. Many of you who have probably actually developed agents before have noticed at some point that the agent is allowed and will go off the rails. Now, someone is asking me about something called CrewAI, and they're probably a little bit ahead of me in the slides, which is the next slide. CrewAI would probably be the second most popular one that I, at least, I don't know the exact numbers, but CrewAI is definitely one of the most popular agent frameworks out there. Now, to be completely frank with you, I am not a personal fan of CrewAI. I'll show you some examples when we get to our code. But in general, CrewAI was the framework I was basically trying to replicate through my own framework because frankly, I could not even get some of the more basic things to work on Crew consistently. And I think that's going to be a key word of today is consistently. It's easy to show you examples of working CrewAI code, but it's harder to show you that same piece of code working 10 times in a row with no flaws. Not to say my own framework will always 100% work, but the fact that it has become such a popular framework kind of leads me to say, well, how are people dealing with the fact that CrewAI not constantly, but consistently will show that it will not complete a task. Now, to be fair, CrewAI is tackling something very complicated. They are trying to make a generic AI agent framework with the ability to work for all different kinds of tasks. So this is not a knock to the actual CrewAI team. What they've built is impressive. It's just not going to work for everybody for all of their cases. Generally speaking, I recommend people write their own agent prompts because if it took me a weekend to do it, I'm sure it can take someone else even faster to make a better version. I'm not the world's greatest coder. My background is in theoretical mathematics. I only learned how to code to do my company 10 years ago. So, it doesn't take that much code to replicate the core features of something like CrewAI. Now, then there's more experimental frameworks like Swarm, and I've never seen anyone actually using Swarm in production, but OpenAI did want to kind of join the hype here, and they put out their own experimental lightweight framework, more about agent handoffs and less about actually accomplishing anything with tools. But I did want to mention it just because it is OpenAI and they tend to lead the pack in a lot of things. It is also a stateless engine in the sense that unlike LangGraph, there is no really such thing as memory outside of the actual conversation in the LLM. There's AutoGen, which I know comes up a lot. AutoGen being Microsoft's framework for multi-agent systems, mostly focused on distributed real-time applications, also written in multiple languages. So you're not just thinking about Python anymore. You're talking about .NET, C#. Of course, it is Microsoft. Microsoft is so old. No, not that old, but Microsoft as a company is so old that the workforce is using dozens of different languages. So AutoGen really is working to support a larger majority of just engineers in general. So at this point is the part where I'm going to say I'm done talking about frameworks, because at this point someone's going to say, but what about B? But what about Letta? But what about blah, blah, blah? Every day it seems like a new agent framework is coming out, blowing things out of the water. And maybe that's true. I don't think it actually is, but are always more and more agent platforms and frameworks coming out. Now, I don't want this to be me just showing you a single framework and how it works. That's really not the point of my time with you today. My point is to try to show you where all of these things are similar, where we can pull out the core components, build our own if necessary, and then move on to how to actually evaluate these systems and make them work consistently at scale. That's really the hard part here, isn't it, folks? All right, so that's kind of our level setting on in agents in general and LLMs in general. I assume most of that was a little bit of a refresher from everything you've seen today and over the last several weeks, but had to be said. So getting started with agents, generally we have to start with the tools, because an agent is really literally nothing without its tools. An agent without tools is basically just a chatbot, an LLM chatbot with the ability to do nothing besides talk to you. And at that point, you're just talking to the LLM. So we talk about tools. Tools at their most basic run with a set of inputs and return and output. Obviously, that sounds really simple, but you'd be surprised how often as a consultant I have to make this very clear. When we talk about a tool has to have a single synchronous run function with a single set of inputs with a more or less single output that can be returned to an agent. Even when we talk about more advanced ideas of agents like computer use, this is still true. Even when OpenAI has their operator, Anthropic's computer use, all of these are still working with a single set of really succinct and concise tools that can do one thing with more or less one set of inputs and return one output. That's what we think about agent tools. So it's not hard to find examples of tools at work. So here is one from CrewAI. All of this code, by the way, can be found on our GitHub, and we'll turn to that in just a moment. But from Crew, you can import built-in tools like Scrape Website Tool. And if you instantiate that Scrape Website Tool, you can pass in a website URL, you run that tool, and then you can grab data from virtually any website on the internet that does not involve any kind of a login feature. You can go more in depth because, as I mentioned, agents are supposed to be working over and over again, selecting tools, running those tools, looking at the output, and finally responding to a user. So in this case, I can use one tool to script a website, a second tool to write that to a text file, a third tool to instantiate a text lookup of that text file, and then query it so that I can grab information from that website. At this point, I can basically build a RAG system with just these three tools, but it would be pretty basic. And we'll see an actually better instance of an agentic RAG in one of our examples. So agents are workflows with discrete decision points, and every point of the agent's lifecycle can be evaluated. Did the AI identify the right tool to start with? Did the AI use that first tool correctly, i.e. writing the correct inputs? Did the tool succeed? That's another part of our evaluation section, which is going to be, well, the tool itself is not technically part of the agent. It's its own separate code function. And if that code function doesn't work and it fails, the agent is kind of out of luck here. It was dependent on that tool to actually do something. So that is going to be part of our evaluation. Did the tool return the right information? Again, does the tool itself function as intended? Did the AI use the tool's output correctly? At that point, you're talking more about hallucinations. Is it ignoring the output from the tool when answering the question? Then if it's going to select a second tool, did it select a second tool correctly? So on and so forth. So every single time an agent makes a discrete decision, taking a tool, writing the input, executing the tool, using the output, selecting the next tool, all of these can be evaluated. And in fact, when we get to our major evaluation time today, we will. So let's turn our attention to Crew. And the main framework that powers most agent frameworks is the React paradigm. You've probably heard of this term already. And if you haven't, I'm here to tell you about it. The reasoning and action style agents, or React agent. You will start to see this term everywhere now that you know what it is. React, which is unfortunately named for the front-end developers in the room, I do apologize, it was not my idea to call it React. The React style agent is effectively what I've been explaining to you. The fact that it has a thought or has a chain of reasoning. It then picks a tool, acts on that tool, looks at the observation of that tool, and then repeats that. So for example, if I say, who is Sinan Ozdemir? That's me. The first thought might be, I should look this guy up. I'm obviously paraphrasing here. It will then act on a tool, look up Sinan Ozdemir. The observation would say, Sinan Ozdemir is an AI expert, author, blah, blah, blah. And then the next thing might say, let me go actually check his website out for info, because if you Google me, you will find my website. So the second tool would be go to sinanozdemir.ai, yada, yada, so on and so forth. And finally, at the end, the system will say, I finally have enough information to respond, and it responds to me. That framework, that React style of agent is, again, virtually how most tool operating agents function. If you use, for example, OpenAI with tool calling or Gemini with tool calling, this is what's happening under the hood. The system is selecting a tool from the list of tools, writing the input to the tool given your function call, your function spec, executing it, grabbing the input, and then deciding, do I need to call another tool, or can I finally answer this person with their question? This is the React style. And not every, but almost X-Men will build off of this framework. And again, if you think about it, this is just really how most people will make a decision. They will have options. They will say, okay, well, what's the first thing I should do? I should probably Google something. They'll Google something. They'll look at what was Googled and say, maybe I should click on the first link. All of those tiny little decisions that we make end up being those discrete decision work points. There's also an example in the GitHub of a Streamlit app that really showcases all of this with Crew, just to kind of give you a visual of what that might look like. So before we turn to our code in just a second, we can also look at this Streamlit app where you can give your agent a name, a role, a goal, and a backstory, and a certain tool. And if you give it a goal, like go to this website and tell me what's going on here, and you give it a rule like give me a short response, and you assign it to an agent with access to that tool, it's going to actually go to that website and look it up. So let's go ahead and take a look. So if you are looking at our GitHub here, you should have access to this GitHub. Like I mentioned, there's going to be way more code than we're going to have time to actually go through line by line. There's at least a dozen or more notebooks here and files here to look at. Now, the first thing you're going to want to do is potentially make a virtual environment, whether you're on a Mac, Linux, or a Windows environment. This is going to be really helpful, especially for packages like Crew. I have heard, not horror stories per se, but I've heard a lot of dev stories of people trying to install CrewAI on their existing environment. Someone is asking for a link to the GitHub. Not a problem. I will happily put that in the chat here. Here you go. There he is. Put it in the chat. I would recommend setting up a virtual environment. Now, in general, in dev and in production environments, they are, oh, well, that's fun. It puts it up on the screen when I say something. I would recommend making a virtual environment. Now, again, we're not going to have time to really walk through hand-holding, setting up a virtual environment. I have done my best to write out all of the steps it would take for Linux or Unix/Windows users. So hopefully this is going to be enough information. And I have already done this on my end as well. But if you have already done this, we can skip down to the actual notebook section, where if you are in that activated environment, so you should be inside of the virtual environment when you run your Jupyter notebook, we should now be able to run all of these code samples. Now, as usual in GitHub, you are free to follow along just by clicking on the link and opening it up in GitHub. Everything has been run already, so you can follow along this way. I will generally be looking at things locally just because it's a little bit easier to kind of shoring up some of the responses. So here we are in our hello world for Crew. And if you've ever used Crew before, you're probably familiar with a lot of this, but just to kind of give you a basic sense for how this works is for how most agent frameworks like Crew will work. You're going to be importing tools from that package. So in this case, I have those 3 tools that I showed you on the slides. Someone is also asking for the slides. Let me do that right now. Copy link, slides. Slides. Great. There you go. Cool. So we have our tools being run here, like I showed before, but let me kind of skip to one where the actual agent is working. This is how most agents are going to present themselves to you. They're going to ask you to instantiate an agent. So here I have the role of, and I'll zoom in slightly here. I have the role of educator, and I have a goal based on the context provided, answer the question. The backstory is you are a data expert. I'm going to turn on verbosity to see what's going on. I'm going to disallow delegation, and we'll talk about delegation in just a second. I'm going to give it my search tool, that thing where it can look up that ai.txt file. So I ask it, understand the topic of natural language processing and summarize it for me. And I say I want the response to be as short as possible. First nitpick of Crew is there are too many places for me to give context. I give it my role, which is technically the name of the agent. That's really what role means, even though the word role is a little bit misleading. I have a backstory here. I have a expected output here. The description of the task makes sense because the description of the task might be different for every single workload call. And then I also have my goal here. In theory, the goal and the backstory here, I don't see why they have to be 2 separate fields. If I wanted to have one piece of context, I would just tell it, you are supposed to answer questions because you are a data expert. Again, a little bit of a nitpick, but I'm showing you this because these are all of the fields that CrewAI lets you set. Now, once you do that and you kick off that Crew, you can start to follow the React framework. The first thing you're gonna, another nitpick about Crew, this is not in chronological order. This is not actually what you're reading from top down, left to right, is not the chronological order of what is happening behind the scenes. They've kind of chopped and screwed it up based on a basically on a stack system. So as the AI is adding things to the stack, you're basically seeing what's getting popped off every so often. So anyways, I give it my task, understand NLP and summarize it for me. So here's our React framework. Here's the thought. I need to find information about natural language processing and provide a complete answer. That's AI generated. Now it's going to pick a tool, search a TXT's content. Now, this is not a, this is specifically, if I have my search tool here, right? Search tool here. If I look at the name of this tool, it is search a TXT's content. This is how the agent knows what tool to actually use. It is literally choosing this phrase, search a TXT's content. That's how it decides what tool to use. So even though we just downloaded or instantiated this tool for us, we can see all of the features here. We have the name, a description, the arguments. So it's basically just describing all of the elements that the agent will need to know, and it's getting injected directly into the prompt. And then it writes this. This is also AI generated, the tool input. And then this is the output of the tool.run method. And this is what it actually returns. We scroll down. And then finally, the agent will give the final answer, which debatably could be its own tool or just the agent built into the prompt saying, I'm ready to give my answer. It gives the answer. So when I check out raw, output.raw, I can see the answer given to me by the agent. Now, at this point, we can make things a little bit more complicated. I can give it basically the same task where I give it a task description here. The only difference is previously I had assigned it to that agent. Now I am commenting that out deliberately. I'm also going to make a second agent called calculator, where its goal is to calculate things. I give it a backstory because Crew tells me to. I also turn on verbosity and still disallowing delegation. And then I add a math task. Tell me what 123 times 34 is. This part doesn't really matter, but I'm trying to write the task so that it's pretty obvious where it's supposed to go. I then start my crew with my two tasks, with my two agents. I also instantiate hierarchical. So instead of sequential tasks, which is the default, and going through them step by step, I'm going to include a manager in the mix. So here I'm letting GPT 3.5 Turbo act as a manager. And the manager becomes a now built-in agent. The manager is given a task, and this is where it's going to get annoying because this is not in chronological order and it's not my fault, I promise you. We can see here the calculator giving the final answer already. But if you scroll down even more, you can see the part where it says the crew manager is, I need to delegate the calculation task to the calculator coworker. And then it's going to choose the tool, delegate work to coworker. This is going to bring us to our topic of multi-agent frameworks. In a multi-agent framework, for the most part, is still a React paradigm. The manager LLM is simply an agent. And the tools it has access to is, as you can see here, delegate work to coworker. We already know the style of the prompt here because we've seen it in the last example. When it says using tool, it's using the name of the tool, delegate work to coworker. And the task, the tool input here, calculate 123 times 34, that wasn't written by me. I didn't write that. That is taken from what I said. Tell me what 123 times 34 is. It wrote this task. So now it's able to summarize my task and give it some context for whatever, again, for whatever reason, it needs more context other than calculate 123 times 34, and it chooses the agent name calculator. We scroll down, the manager also will delegate the understand to the educator, but we've already seen that topic. We scroll down past all of this, and we can finally see the results of each of our tasks being performed. Last example in Crew, just because I want to show a more complete example, or a little bit more complicated example. I can also instantiate tools from LangChain. So I mentioned LangGraph uses LangChain, but Crew, it can also use components from LangChain. So here I'm going to initialize DuckDuckGo search. If you've never heard of DuckDuckGo, you're younger than I am. DuckDuckGo is a search engine, a relatively older search engine, not relatively well used anymore, but technically still works. You are still technically allowed to use DuckDuckGo. And one of the things that I like about DuckDuckGo is you don't actually need an account to run a few examples. If you're just doing kind of your own hobby stuff, you can simply just use it as a stand-in for Google without having to purchase any kind of SERP API or something of that nature. You're going to get limited by the number of searches you can do, but it helps you get going when you need to. Either way, I will instantiate a DuckDuckGo search from LangChain, which has a DuckDuckGo tool already made. So if I run it with a query like capital of Turkey, it's going to give me back a piece of text from DuckDuckGo. Now, I am also now, at least at this point, trusting DuckDuckGo to give me accurate results, which is a topic for another day because the explosion of web search tools like Exa and Tvili actually are not as good as simply just Googling things directly or DuckDuckGoing things directly. So at this point, I have two agents, a researcher and a writer. The researcher is going to give it a backstory, and I'm also going to disallow delegation, but I'm going to allow delegation for the writer. So there's a researcher and a writer, and the writer is allowed to delegate. So now I'm going to make two tasks. Task one is to do a comprehensive analysis of AI advancements in 2024. We still, not too many advancements have happened in 2025, just the one for the most part with DeepSeek and a few others like Stargate. But this example uses 2024. And then the second task is to, using the insights provided, develop an engaging blog. So I make a crew with my two tasks. I set things to sequential, meaning I want things to go task one, then task two. Remember, the writer can delegate. So now I kick off. Here's the problem. If you read through this, which is, again, a little cumbersome, I am aware, the writer at one point, first of all, two things. First of all, it encountered an error when trying to use a tool. But what tool was it? Delegate work. So the writer tried to delegate a task, even though it was pretty obvious which one the writer was supposed to do. It was the writing task is the one that the writer was supposed to do. Even though I assigned it to the writer still decided, no, I'm going to delegate this task away. And when it did, it failed. And you can even see the tool description, delegate a specific task to one of the following coworkers, senior research analyst, which is the only other one besides the writer. And then the actual task will fail because it will keep trying to delegate the task and it just doesn't work. This is and if I disallow delegation and I do everything exactly the same, now I finally get an answer at the end, which is a blog post. Not a good one, but a blog post. So the output of Crew, let me tighten this up a little bit. The output of Crew is pretty simple in the fact that it's just simply doing a React framework. I'll come back to my slides now, but this notebook will go on with building a search agent where we'll do more search agents. I use a custom SERP tool for better Googling so that we don't get rate limited. It will require you to have an account with SERP. I believe they have a free plan. You put your API key here, and the rest of this code should work as is. This is me looking up who is Sinan Ozdemir, using the different tools, the titles, the link, so on and so forth. So that's Crew. Now let's go back here and talk about LangGraph, the other framework I want to talk a little bit more about in detail. So LangGraph is going to expand upon the React framework, and LangGraph actually does have React components available. But the reason I like LangGraph again is that it, actually, question here. I was writing the question below, but now it seems the answer is no. Does Crew use some structured output constraints to ensure that the tool use are always well formed? I don't believe Crew does, Aaron, but I will tell you LangGraph does, because LangChain does. It's actually one of the features I really like about LangChain and LangGraph is that it does actually let you use that structured output, assuming the LLM under the hood, which for most people is OpenAI, allows you to set that kind of structured output. So before we show LangGraph, I'm going to also show, because what I wanted to show with LangGraph is some more expanded agent paradigms. So instead of simply talking about React, where it just picks a tool, executes the tool over and over again, there's going to be two main extensions to this: plan and execute, and reflection. I think you heard about reflection in the last talk, so I won't talk too much about it. But with plan and execute, the idea is instead of a single large, powerful LLM kind of slowly working its way through that thought, action, observation loop over and over again, the idea of plan and execute is, what if you made a large LLM basically make a plan so given a task, write down a plan. And then for each of the steps, a faster, smaller LLM is given discrete chunks of that plan to execute. So visually, it would look like I ask my system to, again, who is Sinan Ozdemir? The first thing it does is it makes a plan. It goes, okay, 2 steps. I'm going to look up Sinan Ozdemir. I'm going to summarize what I find. And then it sends that plan to a React agent, a smaller React agent, to say, look, you don't really have to think through what to do. I've given you the steps. All I need you to do is execute one or more of those steps. So the smaller agent executes the step, returns the output to the bigger LLM. The bigger LLM says, okay, great. I've made a plan. I kicked off the task, the workload, to a smaller agent. I get my observation. Now my job is to say, are we done? Do I need to rewrite the plan? Are there further steps that need to be taken? Or is this enough information? So you see all the elements of the agent are still here. There is still working through that loop. The only difference is the loop was decided up front, and then the loop can be edited as things go. But the difference is we're not really relying on this larger LLM to pick the right tools and execute the tools. That's going to be offloaded to a smaller, faster LLM who doesn't really need to think about what to do. It's literally being told what to do by the large LLM. So the components of an agent are all still here. I'm just kind of chopping and screwing them to try to offload some of the work to a smaller, cheaper, faster LLM. I'll do the code in just a second, but before I show you the code for that, I'll also talk about reflection agents. I can show you both of those in the same code block. Uh, a different paradigm, which is a little bit simpler than plan and execute, is reflection, where the basic idea here is you still have basically a React agent. It doesn't technically have to be a React agent, but assuming it's some kind of agent who can plan and act in tools, doesn't really matter. It can be any kind of agent. The difference is with the reflection component, once the agent is done, it's not actually done. The agent will say, I have my answer to the human. But before it's passed off to a human, basically a QA agent comes in. We call it reflection, but it's basically a quality assurance check comes in. That agent's only job is to look at the goal, maybe look at the steps, and look at the final output and say, is this good enough for a human? Again, the idea here is we are offloading succinct, discrete, mutually exclusive workloads onto other agents who don't have to think about other things. As we talk more and more, you may be wondering, why not just let the world's smartest AIs, call it DeepSeek, call it OpenAI, call it Claude, why not just let them work through the loads? Even money and speed aside, is it not good enough to give those large AIs just access to my tools? And the answer is it might be, but as we get to our evaluation section in our second half, you're going to see that actually no. Even for what seems like pretty simple tool selections, the agents, the LLMs rather, are going to fail relatively more spectacularly than you might think, and for a very specific reason that kind of underlines one of the main problems with AI agents today being based on the transformer mechanism, that seminal moment from 2017 that powers virtually all LLMs that we see on the market today. Question here from Sanjay, is this similar to the hierarchical flow, the planner agent being similar to hierarchical flows? Kind of. The difference between hierarchical and crew is that the hierarchical decides which tasks go first. So in this case, we don't necessarily have different tasks. We have a single task. But instead of breaking it down, so in our example, we broke down a task into multiple steps. We did that ourselves and then gave crew all of the steps. In plan and execute, the planner agent is writing the tasks itself. It's given a singular goal, and then it writes all of the tasks to be executed in order. So in hierarchical, it's deciding which tasks to do first. In planner, the AI itself is generating the steps and executing them in order sequentially. I hope that makes it a little bit more clear. All right, let us look at some examples of LangGraph. There are many, I will say. There is an intro to LangGraph here, which is here. The intro to LangGraph, I think, and I will admit, I took this from LangGraph's documentation as inspiration. I tightened it up just to make it a little bit shorter and hopefully easier to read from there. But just to credit where credit's due, I did actually get this idea as a hello world example from LangGraph, but I'll show you some other more complicated ones as well. So this is CRAG. Welcome to the world of acronyms and AI, folks. Corrective Retrieval Augmented Generation. Coming back to the idea that even LangGraph admits that retrieval augmented generation is agentic. It's to a point where it is a demo that they give of their agentic framework. So kind of going through this idea, the idea is you ask a question, you retrieve documents, you grade those documents as to how relevant they are. If any of the docs are relevant, you can answer the question. If any of the docs are irrelevant, maybe you will rewrite your query and try to find some more information. Now, at this point, it can be anything you want, and how you end this statement is going to be up to you. To simplify it slightly, I've taken their example of their CRAG, where I took 3 different URLs. Ahead of time, so this is pre-agent execution, I load them up into a retrieval system. Now, at this point, it can be Pinecone. I'm using their local Chroma database. I'm going to assume that retrieval is given to us. We are not going to be building retrieval from scratch. If you want to, you can take my other courses. But for now, we are taking retrieval as a given. We are able to retrieve information. However, the problem with a lot of that retrieval is what you retrieve might not actually be relevant because, spoiler alert, embeddings are not actually dense embeddings are not perfectly able to encapsulate all the semantic information from the raw input. So we can't really rely on something as simple as cosine similarity to give us proper document retrieval. So, but in any case, if I ask a question like, what is few-shot learning? I ask it to get some documents and it will give me chunks of documents from a URL. Again, this is just a given that we have access to this kind of retrieval. Now, to actually make the agentic part is how we make the LangGraph graph itself. Now, if you're not familiar with graphs, just in general, nodes and edges and things of that nature, I will admit this is going to be a little bit of a getting thrown into the deep end. But if you bear with me, the basic components of a LangGraph system is we're going to have a data model where the data model is going to be a graded document. So for example, a grade of a document is going to have a binary score, which is going to be whether or not a document is relevant to a question, yes or no. Now, coming back to, I believe it was Aaron's question, if I instantiate an LLM, so standard kind of GPT-4o mini, I can set my temperature to 0 here to kind of make things more consistent and reproducible. I can then create a grader with the LLM with structured output grade documents. This is, again, why I really like the, so Somia is actually asking, I think maybe using Pydantic to enforce constraints before tools. Here you go. This is me using that enforcement to make sure that the LLM will answer given this data model. So the output of this structured LLM grader, and I hope that's what you mean, what you meant, Somia, from your question. I hope this is what you were asking about. So with this prompt, give a binary score, yes or no, to indicate whether the document is relevant to the question. I can set up my prompt here and saying, okay, that's my system. My prompt is then going to be, here's the document, here's the question. Now, at this point, we'll talk about prompt engineering in the next section and how to make these prompts better, but simple prompt here. We then instantiate a pipe where we go from the grade prompt to our structured grader. So for each of the documents that we just retrieved for that question, I will grab the document's text and I will invoke the grader with this question and document, which will get passed into, this is the standard format for variables. So if you put them in curly braces, that's how it knows how to put them in with these variables. I get a binary score of yes or no. What I'm literally getting back is a document. I'm getting back this grade document data model. So now I can grade documents. I will now pull a RAG prompt. I will pull this prompt here where it says you are an assistant for answering questions. This is what's going to be answering our final questions, where I give it a question, I give it some context, and I ask for an answer. Again, very basic prompt here. So I set my LLM. I will just helper function to format our documents into a single string. I then make my RAG chain. So my prompt for my RAG will go into this LLM, which could be the same one, could be different. This is the point where maybe you'll have a Claude here instead of OpenAI. You can experiment with different ones. And that's going to get passed to a standard output parser, meaning it's just going to print something to us. And if we invoke the RAG chain with the documents that we got, with our question, we get back an answer. Great. So we're building our components. Our question rewriter, I'm going to use a different LLM because this is, I would say, an easier task. So I chose a quote unquote less smart model, an older model, ChatGPT or GPT 3.5 Turbo. I write up my own system prompt. You are a question rewriter that will rewrite a question. Given this question, formulate an improved question. I similarly invoke it. I could make a data model here for all of these, but generally when the output is just free text, I don't have to, but you could also use structured outputs here. I just chose not to for what it's worth. I then invoke our pipe with our question. Our question was, what is few-shot learning? And then I get back a rewritten question. What are the key concepts and applications of few-shot learning in machine learning? The idea here is if I ask a question, and that query yields no relevant documents from our grader, I will then rewrite the question so that I can try RAG again, basically. I will try the retrieval again with the rewriting question. So once we have all the components, we can make our graph. So our graph is going to be generally speaking, our state graph is going to be a typed dictionary where we have the state of the graph is going to have a question, our generation, the documents that we're going to be using, and the number of times we have transformed the query, which we're going to keep track of, because if it hits an error state like too many times transformed, we're going to exit the graph and say, we messed up, we're so sorry, or whatever you want to do in that situation. So I'm going to make some functions here. So every single LangGraph function is going to take in your state. This is our state. It's going to take in this object of graph state. So we should always be able to have access to these variables. So here, when I call state question, I'm literally calling it from this typed dictionary. So I grab our question, I then get relevant documents and return document question times transformed. It's generally a good idea to have all of these outputs be elements in your state graph. It's not necessary to do that, but it will make things a lot more readable if the actual variables in your state match what your outputs are returning. Generate, we'll grab in the state. As always, we'll take in the state, we'll grab the question, the documents, it will invoke our RAG chain with our context, our questions, and return document, question, and our final answer, which I'm calling generation. At this point, all I'm doing is using the components we've already built and applying them to our state. So I built out modular components at the top. I'm now defining actions inside of our graph through these functions and outputting them through our invocation of our components. Transform query takes in a state, and by the way, these doc strings are just for us. These aren't actually used by the agent just for what it's worth. I'm trying to be verbose here in our examples. I will grab our question or documents. I will increment the number of times we have transformed in our state graph and return that back. I will write a better question and return that and replace our question with better question. Our grade document similarly grabs our question and our documents and will grade each one. If there is no graded documents, I will also set something called web search to be yes instead of no. Note, this is the only time in this example that I am using a variable not in our state. Now, as I mentioned, you should have everything in their match, and I still stand by that, but just to be explicit, you don't have to. You are allowed to return something not technically in the state graph itself. So here's me proving that you don't have to do that. I will just recommend you do that for all of your at least your major variables, but I can't stop you from doing whatever you want. Decide to generate, we're almost done, I promise. Decide to generate is going to take in our question, take in whether or not we want to do a web search based on whether or not we have relevant questions up here. And we will decide if the web search is yes, it's going to return should generate. If is not, we're going to say should transform query. And if we do have an answer, we're going to return should generate. This is technically an edge, and we're going to put all of these together in the next cell block. So to build our graph, I know this is a lot of code. This is probably why a lot of people shy away from something like LangGraph and turn to a more less code solution like LangSmith, which is the kind of hosted version of LangGraph, which is to say you're basically just dragging and dropping nodes around instead of coding them up yourselves. But it's really all the same thing under the hood. So I instantiate a state graph. I call it workflow. This is our graph state. I will then add nodes. Note, all of these nodes, retrieve, grade documents, generate, transform, query. These are all the functions I just wrote. All of these nodes take in the state and output a state modification. To build the graph, I will add a start node. This is a built-in start node from LangGraph. And the first thing we're going to do is retrieve, given our question. Then we go from retrieve to grade. From grade, we have a condition. Because once we've graded, we might need to transform the query, generate an answer, or do a web search. That's this decide to generate function that we wrote up here. And given what it outputs, like should transform, go to transform query. If it outputs should generate, go to generate. And then we add from transform query to grade and from generate to end. This is all probably hard to read. Well, one nice thing about LangGraph is, I will skip for a second, is that for any of these LangGraphs, we can actually display the graph, which makes it a lot easier to kind of see what's going on here. So here we start with our retrieve. we grade all of our documents, and given the output of this function, if it should generate, it goes to generate. If it should transform query, it goes to transform query. Transform query always goes back to grade documents. So we're always constantly doing this until we get to our generate at the end, and then it stops the graph. So if I ask a question like, what on earth is few-shot learning? To kind of see the traceability here, we end up with our question. We're in the retrieve node. It grabs these documents and it grades them. So it only gave a yes to one of them, but because one of them was graded, it ends up in generate and answers the question. If I ask a different question, like how big is the moon, it will try, nothing is relevant. It will transform the query. It will keep trying until it hits the, we have transformed 3 times, generate. And then at this point, I let the LLM actually answer the question, even though it found no documents. But you could update your prompt here to say, don't actually do that. I don't want you to do that unless you actually found a document. That's completely up to you. So building a LangGraph can seem daunting. I completely agree. At least a lot more than Crew, where you're really relying on the LLM to come up with a lot of those rules. Whereas in LangGraph, I'm really writing those rules for the graph instead. I'll show you a more complicated example of LangGraph agents where it actually does use React in I would argue, a pretty interesting way. As the name suggests, I'm going to make 2 React agents play chess against each other. So this is a relatively long notebook that goes into using the chess SDK, our chess package in Python, where you can render a board, you can tell it to move pieces, so on and so forth. What I'm going to do at the bottom here is I am going to make some tools. So installing LangGraph, importing LangGraph, I have my OpenAI key. I will instantiate a small model and a bigger model just for the sake of being using 2 different LLMs here. I'm also going to make 2 different tools. I'm going to use one tool, and by the way, this tool decorator comes from LangChain. So I can write this function called agent get legal moves, and I can show it's going to come back as a string, and it's going to have a description, a list of legal moves in a UCI format. So it's going to grab the list of legal moves in a board and return what the possible moves are. That's it. Then I'm going to give it the action to move on the chessboard to say, well, I wrote a function above called make the next move, and I have a list now of 2 tools, get legal moves and make an actual move on the board. So now I'm going to create 2 React agents. And if you're wondering, where am I getting this React agent from? This is actually a predefined function in LangGraph. Now you can change the prompts here if you want, but we can even just use the React prompt as is. You're not going to be surprised if you look at the React prompt, it's going to have that thought action observation loop, just like we saw in Crew. So I have a white player and a black player, and I give them a state modifier that just says you are their system prompt, basically. You are playing as white or you are playing as black in a chess game. I give both of them a different tool. I give the black player the bigger model, meaning GPT-4o. I give the white player the smaller model, i.e. GPT-4o mini, to make things a little bit interesting. Maybe I'm giving a bias to the black player. I give them both the same tools, though. Both of them can look up the tools and use them. So I have our simple React agent here. And if I ask the white player to make a move and try to win the game, it will just start calling get possible moves and actually move the board for it. So as a last example here for LangGraph, before we come back to our slides, is I'm going to make a graph. I have a chess state, which has both the next player to play, reading white, black, or finish, messages, which is a very common technique in state modifiers here. So here's going to keep track of all the messages going back and forth through LangGraph. And I'm going to make a new agent called the referee, or the game supervisor. It's going to manage the game between 2 players, alternating turns, and decide when the game is over and respond with finish. So our supervisor node is going to have our messages start with white, because white will go first in every game. And if the game is over, it's going to say who the winner is, render the board, and basically say finish. The white player is simply going to invoke the React agent for white. The black node is simply going to invoke the black React agent. And if I build this, it's simply going to be, I have our supervisor, our white agent, our black agent. Start with the supervisor. The supervisor will then, if it's white's turn, go to the white agent. If it's black, go to the black agent. Those are the names of our agents up here. And from white agent, go back to supervisor. So every time they play, it goes back to the referee, basically. If we look at our graph, it gets more complicated. Now I have two different React agents, one for black, one for white, and a supervisor node up here. So if I actually run this and say, just start the chess game, and I send that to the supervisor agent, it's going to literally, zoom out here, it's a little bit easier, it's going to pass it back and forth. Black will move, then white will move, so on and so forth, until black makes a move, and then it's game over. Black wins. So remember, black was the one I gave the larger LLM GPT-4o. Now, I'm not saying black is going to win every single time here, but the fact that we do have the two different LLMs makes for a more interesting conversation. Now we have this ability to choose between how these agents are going to interact with each other, and this kind of back and forth between the white and the black agent makes it more interesting. Now, there are also two examples here of plan, execute, and reflection, where we have plan, execute. Zoom in here. We have plan, execute, also using the create React agent node like I did in our chess graph. I will pull the React agent executor. We have our messages here. Our LLM, we create our React agent with the prompt that we pull from the LangGraph hub. I will then ask, this is going to be out of date, but I did put a date on when I last ran this for this question. I'll say, who won the most recent Ravens game? And as of November 19th, it will say correctly that the most recent game was Ravens losing against the Steelers. So this React prompt seems to work. And all I've given it was access to the only tool of DuckDuckGo. So it can call the tool, look it up, and respond something. Easy. So then I have to make a planner. The planner is going to be a base model with steps here. My planner prompt is going to say, for the given objective, come up with a step-by-step plan, which is going to get passed into our structured output here as a steps which is a list of strings. So our planner prompt is going to get piped into ChatGPT or OpenAI GPT with the structured output of plan. Again, our plan-based model here. So if we invoke, what is the hometown of the QB of the winner of the most recent Ravens game? I worded it in such a way that it would need to be broken down into several steps. Step 1, identify the most recent game played by the Ravens. Step 2, determine the output of the game. Step 3, if the Ravens won, identify the starting quarterback. Step 4, research the hometown of that quarterback. Now, I didn't write this. This is completely AI generated. So I don't think this is the best, the most succinct plan possible, but we're going to take it at its word. The next thing we'll do is a replanner task. So given the objective, which is we're going to put in here, and the original plan, I'm also going to pass in what's already happened, and I'm going to ask the planner to update the plan. So with that, it's going to output this class act. Well, that's funny I said that. A Python class called act, whose output is action, which is either going to be a response or a plan. That's what union means here. It's either going to pass back a response, which is just going to have a response string, or the same plan object we saw previously, depending on what is going to be outputted here. So by outputting here, now our structured output could either be a response or a plan. So if we invoke the replanner with what is the hometown of the QB with our current plan and the past steps, so in this case, let's say I've already answered, identify the most recent game, they played the Steelers. I will then say, give us the new plan, and says, okay, determine the outcome of the game. If the Ravens won, research the hometown. This looks the same, although it's technically different. instead of determining the output of the game between the Ravens and the Steelers, it didn't know this before. The original plan was determine the outcome of that game, win or loss. So it's updating its plan with the new information. So we build our graph, plan and execute, which is going to be our state, our input, our plan, our past steps, and our response. Our execute step is going to get passed into our plan. It's going to invoke the agent executor and then return, these are the past steps that have been run. It's probably easier to watch the actual graph here. So it goes to the planner, and then the planner goes to the executor. The executor is a React agent. That's what can solve each step along the way. So every step is getting passed to the executor, and once that single step is done, comes back to the planner and say, are we good? Like, is this going to actually solve the plan, or do I need to replan, which will go back to the executor? So we're constantly planning and replanning. So if we actually do it, what is the hometown of the QB of the winner? Here's our first plan. It will identify the game, in this case, against the Steelers. It will replan, find out the winner of that game, and then identify the starting quarterback of the winning team, research the hometown of that quarterback. Then it looks up, find out the winner. The Pittsburgh Steelers won the game. Okay, replan, identify the starting quarterback of the Steelers for the game 11-17, research the hometown, so on and so forth. It ends up with Russell Wilson, whose hometown is Richmond, Virginia, which is correct, at least at the time of asking this question in November. Our reflection is a lot more simple, quite frankly. Our reflection graph, I'll just skip to the graph itself, simply looks like this. We basically ask it to generate something. In this case, I ask it to generate a LinkedIn post. It will then reflect on that LinkedIn post, rewrite it a few times until it says this is good enough, and then end. So it's not a much more difficult task of building the reflection agents. In fact, if you were in the last session with Lori, you saw an example of using reflection in Llama Index, I believe. So this concept is not necessarily confined to LangGraph or even to Crew or to Llama Index. It's just an idea that you would have an agent look back on another agent's work and say, try that again, given this critique. All right, let's come back to our slides here because I want to keep things trucking. We're a little bit over halfway done. So at this stage, we're talking about prompt engineering, stuff you've probably heard in the past, but to generate a good prompt, you are going to want to use things like few-shot examples, where you're basically giving in-context learning to the LLM. You're giving the LLM examples of how a task is supposed to be solved inside of the prompt itself. This is so important that the name of the paper from OpenAI that actually talked about language models being few-shot learners has that name directly in the title. A question here from Aaron: to what extent do chain of thought models like O1, R1, whatever, supersede the kind of plan, replan approach? It's funny because the name of that style of prompting is simply chain of thought prompting. That's kind of why they're called reasoning models, because chain of thought reasoning is another name of chain of thought prompting. It can't supersede the actual agentic work here, because while it's thinking, it's just talking. There's no tools. It can't do something and then replan. So the O1 models, the R1 models might be better at replanning, but they're not necessarily superseding the idea of executing a tool, observing the result, and rethinking the steps. You would hope that the thinking simply makes them better at planning and replanning. I'm seeing some, it's so hard to copy and paste things in the comments here. I was trying to look at some of these links that you guys are sharing, but I might have to look at those a little bit later, sorry. So it's no surprise that adding these prompting examples or these prompting techniques is going to make your responses a little bit better, whether you add a few-shot learning or chain of thought prompting. To prove that, just to be safe, I have a case study in my book that I talk about where I use a math benchmark. Very common to use math benchmarks for something like this, where it's very simple. I give it a question, I give it correct answers or possible correct answers, and I ask it to reason through and then think of the right answer. Now, in that case study, I work through about 6 or 8 different models. And for each of those models, I have 10 different prompt variants, ranging all the way from the left to no prompting and just asking the math question and saying, whatever you want to do, go for it, all the way to the right, where I'm using few-shot learning and, more crucially, what's called semantic few-shot learning, where I'm actually using an embedding model to find the most relevant examples from a library of examples, and that generally yields the best results. It quadrupled the performance of Llama 3 on the bottom right, from no prompting all the way to 3-shot prompting with chain of thought. And for Anthropic's Opus, it went from 50% to 75% accuracy on that task. I'm still actively running this task also with DeepSeek because their API continues to be busted because of all the people trying to use it. But I'm also going to update that case study to include more models like DeepSeek in the future. So when it comes to a React framework, we can build our own prompt. So if we have time, if we look at the actual prompt in my notebook under first steps with agents, you'll see that the prompt itself simply has that same loop: thought, action, write the action input, see the observation from the tool, repeat until you think you can finally answer the question, and then respond to the user. And the input would be, what is the actual answer to that task? Now, I'll briefly show this, and I'm going to try again to I wish I knew how to copy and paste stuff from this chat. I don't know why it's so difficult for me. That's fine. In our GitHub, we are going to be looking at first steps with our own agents. This is a collab notebook. This is an example from my book where I basically go through building an agent prompt, where we build our own tool interface to kind of copy Crew a little bit here. I'll clean this up a little bit. We write a tool for Python REPL, which is an execution environment for running Python code, where it has a run command. Zoom in slightly here. With a run command with a set of Python inputs. And we also will make a SERP tool, which will Google things, basically. And so here, if I ask my SERP tool, who's the current Ravens quarterback, this is still correct, Lamar Jackson. If you couldn't guess, I lived in Baltimore for a while. That's where the Ravens are. So then I'm going to basically, just to kind of copy and paste what other frameworks are doing, I make an LLM class just like LangChain has, just like Crew has. Again, not that complicated. I have a generate function. I will optionally have a warehousing functionality where I can warehouse any of my agents' answers to a third-party database. Here I'm using Supabase, a third-party relational database API, so that I can store all the times my agent actually speaks and does something. So my LLM, if I ask it, I'm simply just asking it a question now, like, who is the president of Turkey? No Google, no Python. This is just me asking the LLM a question. And then here's our prompt. I give it today's date, which is usually a good idea in most prompts anyways. And I say you can use tools to get new information. Respond to the user's input as best you can by using the following tools. I have a place to put the tool information. I then give it a pattern to format. This is our few-shot learning. I give it our input, thought, action, input, observation, thought, action, all the way to I have enough information. It then gives me my final response. This is our chain of thought. I'm asking it to say, I have enough information. Now I can finally answer the question. And then I say go, and then I give it the past messages. Our agent class is simply going to pass in some of our variables here, given our tool description, tool names. I give it a run function with a question, which is simply going to loop over and over again, given a max number of loops, format the prompt with all of the thoughts it's had before. I, for verbacity's sake, print that all out, parse the response, literally using a regex. What tool did you select? Is that a name that I can find? And add that to the prompt, the observation, until I see the final answer token, which is the assistant response, the assistant thought from our prompt. So if I ask a question like, please write me a function to take in a number and return 2 times it, here's what our prompt looks like at runtime. And then at the end, show you the actual chat here. It says, I will write a simple Python function. It chooses Python REPL. It runs the input with this Python code, and the observation is 10 because it gave this example of double number 5, and then the response is, here's the Python function that takes in the number. So it actually ran the Python code and then outputs the actual code to me. I'll skip ahead to some more interesting examples where I add in an image generation tool using Stable Diffusion, where I can, input a prompt and it will give me a photo of a cat lounging around. Maybe not the best one, but that's not my fault. So now I have Python, Google something. I added a tool called Simply Respond if the agent ever gets confused about what to do. I asked an inquire, meaning to ask me a question if it needs to, a Stable Diffusion tool, and I gave it access to a fake stock portfolio using Alpaca. So if I ask it, I need a picture of a black cat, I get this, and then I say, here's the image. I say, can you make it in Paris? It remembers that I asked for a black cat, so it rewrites the prompt, sends it to Stable Diffusion, gives me a black cat in Paris. Then I say, what is my stock balance? It gives me a fake number. It's not a fake number. It's a real number from a fake portfolio using the API. And then I can print all those responses. So this is effectively ChatGPT using the exact same LLMs. I've made a prompt just like ChatGPT. I gave it access to the tools I wanted to give it access to. And at the end of the day, it's going to work basically exactly the same. It asks me follow-up questions. It will run tools for me. It gives me my response. It's just going to end up being whatever tools you give it. In my other O'Reilly class where I do retrieval augmented generation, I built an API to do retrieval. So in this case, to kind of, again, continue to prove the point that agents are basically just RAG, I make a tool that will look up information in a Pinecone vector database called a semantic search tool, put that in the description. I have some helper functions here to actually run the query from Pinecone. So in this example, I have indexed the FAQs of the Social Security website on faq.ssa.gov. So when I ask it a question, I lost my Medicare card, it looks up the information on that semantic search, and then it will tell me, I lost my Medicare card. It gives me, oh, sorry, this is the tool. It's giving me the response. I asked my agent, what is the hash of the number I need to call to replace my Medicare card? And if I look at the steps, it says I need to find the contact number for replacing a Medicare card. So it uses my semantic search tool, contact number to replace Medicare card. That's the input it gave. It gave this information. It then says I need to write a Python code. So it runs the action Python REPL. It literally writes code to hash the number it found from the database, gives me this and says, okay, this is the hash I got from running that Python code. Boom. That's our agent. So if you take this to its logical conclusion, and you can see this at this directory, at this GitHub repo here, this is called squad goals. This is the framework that I just showed you as an actual Python, as an actual thing you can pip install and use. In our own GitHub here, I can even show you how it works. So here I am importing squad goals after installing it. It's in the requirements file. I will make a brand new tool here using DALL-E, which is OpenAI's image diffusion tool. So if I make a tool called DALL-E tool, which will have the description, the tool can generate images. I instantiate my squad goals here. It's going to look almost like Crew, right? But I wrote this using the exact, almost the exact prompt that I just showed you with some tweaks. Agents and task, OpenAI LLM. I will use the Google tool that I also wrote in that GitHub repository. I instantiate GPT-4o. I instantiate my two tools. I create an agent with those tools with verbosity on. And I say, make an image of the team mascots of the upcoming Super Bowl fighting. So loop one, it looks up the Super Bowl 2025 teams and then chooses the DALL-E tool with this image prompt, and it gives us this gorgeous image of hopefully the Chiefs losing. Sorry, hopefully. So with that, we can come back to that, the moral of a lot of what I'm trying to say today, which is you should be able to make a lot of these types of agents frameworks yourself. All right, let's move on to our final section here about evaluation, or one of our final sections about evaluation, building and testing the actual agent. So measuring the agent is going to come down to a few factors. Here are a few of those factors here. We have basic things like latency, how fast are the actual tools, the error rates, the cost per task, the LLM error rate. Did it actually follow my instructions? Did it select the right tool for the job at hand? How many steps per task can it take? What is the task completion rate that it is getting? What is the token efficiency? Meaning how much is it rambling, like R1 and O1 really like to do? How much is it rambling before it actually chooses a tool and executes that tool? So there's a lot of factors that we can think about when thinking about evaluating an agent. These are explicit metrics. These are really explicitly measuring the agent itself. Implicit metrics will more come from your system around the agent, meaning if you're having a conversation with someone and you're asking it to, draw me an image or whatever, how often do people drop off that conversation? Can you measure NPS or CSAT, which are metrics for in customer support that will measure how much a user enjoyed a conversation? How often do they copy and paste a response from the AI? I would bet you $100 that OpenAI is measuring how often you click that copy button, and it uses that as an implicit metric to say, well, you probably liked the conversation enough to copy and paste it. That's not always going to be true, but more likely than not, you're probably copy and pasting it because you liked it. If you give it a thumbs up, thumbs down, workflow run rate, you have explicit and implicit metrics. Now, when it comes to evaluating, you're also going to have to talk about some bias here, because you'll notice over and over again that agents are going to stick to a certain style of formatting an answer. And also the agents can seem like black boxes, which is why I was showing you the prompts and the actual step-by-step. I'm thinking about doing this. I am calling this tool. This is the input to the tool that I'm doing. But you only got that from me because I wrote it into my own framework. Not all frameworks are going to necessarily show you that. LangGraph has built-in traceability where on the website, if you are hosting this on Langsmith, you can actually see the moving from node to node, calling different tools, what tool inputs were being called. That kind of thing is going to be quite handy in deciding how you might want to tweak either a prompt or a graph. Also, when it comes to evaluating an agent, because agents are living on top of LLMs, we're basically talking about evaluating LLMs. So let's talk about evaluating two major components: picking the right tool and responding to a human. So picking the right tool is going to be a task called multiple choice, which sounds obvious. You are giving the AI a predefined list of options and asking the AI to pick from those options, i.e. pick the right tool for the job. So far, we've never really given an AI more than, well, in our biggest case, we had, I think, 6 tools in that Colab notebook. But for Crew and LangGraph, we only ever gave it 1 or 2 tools to use. Our free text response is going to be our tool input and our final response to the user. Technically speaking, you could build a classification model to help you pick tools, but most people don't do this. They just rely on a generative LLM to tell you which tool they want to use. So let's go to our big case study of the day, because tool selection and tool accuracy is probably one of the most commonly evaluated things of an agent. So we're talking about multiple choice. So in multiple choice and picking tools, you are asking the generative AI to answer a question, giving a predefined set of options, and how you actually choose that answer is going to affect how you are going to parse the answer. Now, generally speaking, if you're giving it like letter answers like A, B, C, D, or E, you could, for example, just look at the AI's response and say, I think the answer is A, I think the answer is E, or whatever it is. Or the problem with that is you're not going to always get the right response. Now, because we're doing tool selection, it is rare, not impossible, but rare that it's going to just simply not say one of the tools that you are offering. It will happen sometimes, but there are, in general, with multiple choice, more advanced ways, but besides simply looking at the AI's response. For example, you could go off the token probabilities, where you're actually calculating the token probabilities and saying which tool has the highest chance of getting selected, even if the AI doesn't select that tool. But either way, let's assume the AI is just going to spit out the name of the tool, like Crew does, and like our framework, Squad Goals, does. We can think about selection here as a classification task. Well, what's the accuracy? How many times is it choosing the right tool over all the times it was asked to choose a tool? Precision, for a specific tool like Scraper, of the times the scraper was selected, how often was that scraper correct? And recall, which is kind of the opposite. Of all the times the scraper should have been selected, how many times was it actually chosen? These are very standard classification metrics that will apply to our tool selection. So here's our big case study. What I did is also in the GitHub, of course, is I made a list of tasks. And I tried, and you can debate me on this, I tried to make most of those questions pretty obviously matched to one of 5 tools. So for example, I made a fake tool called Crypto and NFT tool, which is, as the name suggests, meant to be only used when looking up crypto and NFT information. So I say, check the floor price of the World of Women NFT. I would expect it's going to choose the crypto and NFT tool. Similarly, I have a Firecrawl tool, which is a third-party service for web scraping. So if I say, go to this website and tell me about it, I would hope it will simply go to that website using the Firecrawl tool. Similarly, I let it Google things. I also give it a Google Spreadsheets tool to add data to a Google Spreadsheets. And I'm blanking on the 5th tool. Let me look. I'll show you. Our tool selection. What was that 5th tool? Why am I blanking? Load. It was, Python. Duh, Python. So if I literally say convert 98 degrees Fahrenheit to Celsius using Python, I will expect it to use the Python tool to run and execute Python code. Now, I should be clear, I ran this test on my own framework because I have complete control over it, and I added in a tool eval mode where I could save time by basically stopping it after it selects a tool and not letting it actually run that tool for us. So because all I want to do is see, was that tool selection actually correct? So come back to our slides here. With that, we can see results of the 10 different LLMs I tried, ranging from Llama 3.2, 3 billion, all the way to Haiku 3.5, Claude 3.5, Haiku latest. And you can see here we have a clear progression in accuracy. Our Claude model, which got just under 98%, seemed to be the best, beating GPT-4o. Now, at this point, you might be wondering, isn't Haiku a smaller model than GPT-4o? Yes, it is. And this is the part where I say, just because an LLM is in theory better than another LLM in most people's conversations, does not mean it's going to be the best for your framework, for your test data. You should always be testing tool selection accuracy because you might be surprised. After I ran this test, I basically switched away from OpenAI to only using Anthropic with a surprise twist in just a moment. Now, to the left, I'm not surprised. So the story here is one of my co-founders for my company was looking at these results and saying, I did not have this one on the left here, because he was saying, I was trying to use the framework, but I was using Ollama. If you're not familiar with Ollama, it's a way of locally running LLMs. And he was using Llama 3.2 3 billion because it was fast. And I pointed out to him that 3 billion is A, not a lot of parameters, and B, they're quantized down to 4 bits. So you're not only getting a worse model that's smaller, you're getting the worst version of that smaller model. So I added it to the experiment to say, to be clear, this is what I mean when I say maybe don't use the quantized 3 billion parameter model, because it literally gets an abysmal performance of 25%. Llama 3.1 and Mistral, which are roughly 7 and 8 billion parameters backwards respectively, get 81, 83%, respectable. Gemini got roughly 90%, and it climbs again up to Haiku. You can also look at a precision recall heat map for all of these models. So for each of these squares, you're literally looking at, for each of the models, what is the precision recall for a specific tool? For example, the SERP tool here on the last column of the precision heat map, looking at this 0.62 where my cursor is, that means that llama 3.23 billion, 62% of the times when it selected SERP, it was incorrect. Now, why was it incorrect? This won't tell you. This is just telling you when it chose the SERP tool, it was incorrect. It might have been because it was incorrectly selecting another tool it thought it was supposed to use. But these maps will just give you a sense for which tools are not being utilized correctly. That kind of leads us to one of the biggest reasons why tool selection is not going to be perfect, even with a model like Haiku getting 98%. So if you think about a prompt in these agentic frameworks, we think about our general instructions. We then will have a section for the tools, just like ChatGPT does, just like Crew does. All ChatGPT, Crew, and our framework all work the exact same way. And then there's the actual conversation history below it. There is a problem with our current architecture of LLMs, and it's called a positional bias. That positional bias generally means that items that are earlier in the prompt, i.e. just more at the top of the prompt, tend to get over-selected versus things lower down in the prompt. So to test this, I did that exact experiment I was showing you, but what I didn't tell you was, for every single one of those questions, I asked the model, each model 10 times. So 10 times 10, each question was asked 100 times to the models. Every time I shuffled the order of the tools. So it was never the same order, or it was at least a random order of the tools. And I kept track of the right tool index and the actual chosen tool index. And I got this graph, which shows that for every tool index, there were only 5 tools, so there's 0, 1, 2, 3, 4. For every index, the green bar is how often that tool was the correct tool. The orange bar is how often that index was selected. Didn't matter what it was, that index was selected. And you can kind of see what I'm talking about just from this graph alone. For index 0 and 1, they were over-selected more than they were correct. And starting at 2, they were getting under-selected. So put it another way, an average across all 10 of those models would show that overall, the first index of tools was over-selected by roughly 10%, and the last index of tools was under-selected by also roughly 10%. So this pattern seems pretty alarming. Well, alarming in the sense that it's showing us why tool selection might be off. It might not be because your descriptions aren't good enough. It might simply be because the architecture of the transformer has a fatal flaw of positional bias. Now you might be thinking, Sinan, that's not fair. That's probably because those terrible 3 billion parameter models, not necessarily. OpenAI alone has this positional bias. Google, unfortunately, had the worst positional bias. We're over-selected the first index by roughly 27%. I have the wrong graph name here, I apologize, but I ran this yesterday with DeepSeek. With DeepSeek, which by the way got 98.94% accuracy, so it even beat Claude Haiku here, but even it shows some positional bias. Of the times where it got it wrong, albeit in that 1% where it got it wrong, it over-selected the first index and under-selected that fourth index, I should say. So even the really good models getting 99% accuracy, part of the reason it's getting the tool selection incorrect is not because of your prompt. It's not because you're describing your tools incorrectly. It can be because the underlying architecture is unfortunately pretty fatally flawed by a positional bias. So now we can talk about assessing the actual quality of the free response, not the selection of the tools itself. So we're in that free text response area. So you could have something like ground truth and use semantic similarity to compare that to some ground truth. This works, but it requires you to have a ground truth for every single one of your responses. I think a better way to do this is through rubrics, which will involve you at home or wherever you are, writing a prompt telling the AI what you are looking for in your response. If there are reference answers, how well does it compare? How natural is the answer? How well does the answer the question? How safe is the answer, whatever that might mean to you? This is obviously a sample prompt. I give it few shot examples of how I want my response to be. I give it my query, my references, my output, and I say, give me your answer. Yes, I could have chosen a structured output here, but if you're not going to be using OpenAI or something with a structured output, I wanted this prompt to work for virtually any LLM that you wanted to try to use. But be aware that depending on the model that you choose, will give different responses. Here is a response to the question, what happens if you eat watermelon seeds, to 3 different models, GPT-4o, 4o mini, and 3.5 turbo. They all gave different responses, ranging from 8 on average to almost 10 on average. Now, if you think this question is weird, this is actually a question from the benchmark Truthful QA. If you've ever seen that Truthful QA benchmark, this is one of the questions in that benchmark. So I didn't make this up. This is actually a benchmark from OpenAI. So I'm not saying one of these models is correct, but I am saying that you are going to want to check which model is actually matching the scores that you would have given that response. That same prompt will yield different responses depending on which model you choose. It's not just pick a model, that's it. I'll skip the code for this just because it's just running a prompt against a question, because I do want to move on to our actual final segment just to make sure we're doing okay here. Yes, our actual final segment before we get to our next steps here is evaluating the actual agent components itself. So one of the things you're going to want to do eventually is have 2 different agents executing the same goal, and you're going to want to compare the outputs of those 2 agents. Now, I'm still assuming that the outputs of your agents are going to be roughly some kind of a free text response. So if I ask it, tell me about Sinan Ozdemir, only make one web search, this is using our framework here, it's going to use the SERP AI tool and return a response to me. If I say make multiple web lookups, it's going to use the SERP tool twice and then give me a final response at the end. But what if I want to compare those 2 responses to say, well, do I want to tell my agent to only make one web search or make multiple web lookups or whatever the difference might be? To evaluate between those 2 options, I could ask a human, which of course we are relatively expensive and it takes time for us to do this. And if you're going to ask multiple humans, i.e. judges, the main issue is going to be finding consensus. Or you could do LLM as a judge, where the AI is going to be given the 2 options and pick which one is better. However, the main issue here is AI bias. And I don't mean necessarily a values-based bias. I mean, here comes the positional bias again. A very common prompt to do something like this would look like this prompt on the screen. This is actually taken from Hugging Face, an article from Hugging Face. And when they did this, here's an example. We said, here's a question, here's assistant 1's response, and here's assistant 2's response. You give it a chain of thought, and then you let it answer which one is better, the first one or the second one. And I actually, what I'll say is actually asking to give a score between 1 and 8, or 1 and 9 rather, where 1 means I strongly prefer assistant 1, and 9 means I strongly prefer assistant 2, and 5 means they're both roughly the same. Even then, when I'm just saying pick 1 or 2, it still picks a number that strongly prefers the first element in the prompt. Look at the title of the graph. I also did this only for ones where humans gave both of the responses the same exact score. So humans came to a consensus that both responses were equally valid to the question, but even then, the AI said, nope, I like the first one better. That's also a positional bias. So you might be wondering, well, then all hope is lost. What can we do? Well, there are things we can do to mitigate a positional bias. One thing you could do is have chain of thought. So a modified version of that prompt would be rate the performance of 2 assistants in response to the user question. I say, give it a score of 1 to 3. where 1 means you strongly prefer assistant 1, 3 means you strongly prefer assistant 2, and 2 means either one will work. So I simplified the prompt and I gave it both responses here. I also gave it the option to use the prompt with or without chain of thought. So with no chain of thought, it would say the score is 2, the middle one. With chain of thought, it would actually walk through, well, assistant 1 provides a clear and concise summary. Assistant 2 has a more extensive and structured overview, including career, academic contributions, and area of expertise, making it more informative. And then it chose a score of 3, which means assistant 2. And when you look at that response, you will see that without chain of thought, in blue, it almost never chose the option for 3, where assistant 2 is the best. It almost always chose options 1 or 2. That's a positional bias. It is actively under-selecting a later element in the prompt as opposed to the first one. And I should be clear, I tried this 100 times with these same exact inputs. Or I just swapped them back and forth between which one was first and which one was second. With chain of thought, the scores were more distributed. Now, it's pretty obvious still in orange that there is still a positional bias where it's choosing 1 over 3. But at this point, I have no way of saying, well, it could have been statistically possible that well, I should be clear. I made it so that it was always the same amount of times where assistant 1's was the first one and assistant 1's was the second one. So it should be, in theory, choosing them equally. But even with chain of thought, I'm still getting an over selection of assistant 1. But we can definitely still see with the chain of thought, it is more likely to actually, quote unquote, correctly, at least favor, in some cases, assistant 2. So proper prompting doesn't just make agents better, it makes agent evaluation better. So when you are judging these, it will make it better if your agents are as simple as possible. And I realize that statement itself is oversimplified, but the reason I made my own framework here was because when I tried to use Crew for my own personal use, and I tried to do this kind of evaluation, like how well is Crew's prompt choosing the right tools for the right moment, I found it quite difficult. I similarly found it difficult to well, that was the biggest thing I found difficult because getting the output at the end was pretty simple enough. So in general, it's going to work to make whatever framework you're using as simple as possible, even if that literally means making your own. Make your own framework. The hybrid here is LangGraph, because LangGraph is going to provide you that way of structuring your agentic workflow in a graph while still having the options of changing up the prompts and seeing how well that change will affect the outcome of the system. So human evaluation will be better at first, presumably, and give you a higher quality, whereas LLM evaluation with a prompt can obviously scale up, but it's going to have a problem with bias. Before we get into our future trends with AI agents, let me go ahead and show you some of the code for those rubrics back to our GitHub here. So that, like I said, this notebook shows you that test for tool selection being done. I would argue it's not very interesting, quote unquote. It's just literally running through a bunch of options, and that's where I create the graph itself here. I will note that there is a secondary notebook that does the same. Oops, my markdown is broken here. I will have to fix that. There is a second notebook that does the exact same experiment using DeepSeek that I literally only uploaded 6 hours ago when it was done running. So same questions, same fake tools. I go to the end here. Probably should have printed that. I'll remove it. And I tried 3 models. I tried DeepSeek Chat, which is not R1. It is V3 in the API because I literally cannot get R1 to work on the API, and I don't want to use the quantized version. I would rather use their own API. So, but that 98.94 was DeepSeek Chat. I did try on Ollama the distilled Quen model using DeepSeek Chat, and it got a worse score than even Llama 3.23 billion. And when I tried the distilled 1.5 billion model, I got 0.17%. This is going to make a bigger point about DeepSeek, which is to kind of Aaron, I think it was Aaron's question earlier, how will their planning actually supersede this kind of planning and executing? To DeepSeek's, in their own words, these models are not actually going to be very useful in day-to-day life yet, because those 5 benchmarks that it was showing that everyone likes to talk about, those complex reasoning benchmarks, no doubt is impressive. But according to my own framework or my own testing of my own framework, I can't make them think through selecting the right tool. And I even like read through at least half of the examples here just to make sure that my numbers weren't wrong. It just rambles on and doesn't actually select any tool by name. It will say, I'm going to Google this, and then says, I Googled it, even though it didn't actually Google anything. It just thought it had Googled something. So it didn't actually follow anything that I wrote in my agentic prompt. So even though these models are impressive on one hand, they don't seem to follow any kind of prompting instruction, especially for an agentic use case. So this DeepSeek chat, and the reason the DeepSeek chat worked so well is this is not a reasoning model. I'm actually very curious to see when I get access to R1 API, how well it will do, because the non-reasoning DeepSeek model beat everything that I had tried before. But I have a sneaking suspicion that the R1 version is not going to win because of that rambling feature of the AI itself. All right, a couple trends here to kind of close us out before we move on to some final questions. Future trends in agentic work will mostly be pointing to things like computer use, where we have things like Claude and now OpenAI's operator running these kinds of computer machines. Now, as I mentioned before, even the computer use itself is going to be that discrete workflow. So every time you ask a model, OpenAI's operator or Anthropic's computer use model to do something, what happens under the hood is, first, it's going to pick a tool. There are literally tools. The tools will be things like move the cursor, click the cursor, execute a shell command. These are actual tools in the prompts of these AIs. And every time it selects the tool, the input then are coordinates, where it says move the mouse to these coordinates, and then click the mouse. And every time that happens, the observation is the screen. The screen is sent back to the LMM, the large multimodal model, so it could be Claude or GPT-4, and then it repeats. So are definitely more impressive than anything I've showed you today, but still the exact same React framework. I give it a singular task. It will consistently pick a tool, move the mouse, click the mouse, look at the screen, decide what to do next, and finally say, I've done it. And even though the LMs are bigger, it can process images, the tools are more interesting, it's still the same exact React framework. Building these kinds of agents yourself can also be depending on whatever parser that you use. For example, OmniParser by Microsoft is a tool for parsing screenshots. So if you don't want to use a large multimodal model like GPT-4, you could use a model like OmniParser to parse a screen, send the screen elements back to a text-based LLM like DeepSeek, and say, run the machine, given these coordinates from OmniParser, and go on from there. Outside of computer use, we can see agentic work being used in a lot of different cases. I'm not going to kind of beat that point anymore, that you've probably already heard it. I'll skip to something that I think I'm waiting to see are truly collaborative multi-agent systems. The best multi-agent systems I've seen today are ones explicitly designed by developers using something like LangGraph. So by sharing the load across multiple agents, whether it's planning and executing or a white agent and a black agent in playing chess, you can save on your context window your messages by not having a singular agent having to think through over and over and over again. Similarly, you can have multiple experts all being tasked with certain types of tasks. For example, you can have a Spotify agent who has access to all things Spotify. I would bet that this is going to be some phone company who is putting AI on our phone is going to eventually have different agents or experts, all good at handling a certain amount of tools for a specific app. I can't imagine what is going through Apple's mind when they're trying to put these LLMs on our phones and saying, what are all of the tools? Are they all of the apps? Is it that visual computer use style? How will it know what the tools are going to be? And if there are more than 5 or 10 tools, as I showed you in our example, positional bias will rear its head. How are they going to deal with it? Maybe they'll use classification to select those tools outside of just generating the response. I don't know how they're going to do it, but those are all questions that they're going to have to answer just like us. That real-time collaboration between agents, yes, and simpler UIs for generating agents. I think this is already happening with these proliferation of agentic platforms and not just frameworks. Auto generation of tasks, kind of alongside planning and executing, is, well, what if you don't need to even tell the AI what those steps are? How well can I plan and execute agent auto generate different tasks to run without me asking it to do so? Similarly, auto generation of tools would be quite interesting as well. Computer use gets around this by saying the tool is simply navigate a machine, and the observation is the machine's output. But for example, if you're a developer and you have documentation for a list of APIs, it would be sure nice if I could use an agent to say, here's documentation, turn these into tools, given a token, or look at the authentication flow to go get a token if you need it, and turn that into tools itself. So going from documentation to a list of tools would also be an interesting future trend. Auto generation of agents. What if an agent's job was to spawn more agents, to say, I need help to split up this work. I'm going to create an agent with its own backstory, with its own set of tools, so that I can call upon it. It's all possible in theory. If I have a manager LLM, instead of giving it workers, it can say, I'm going to make my own worker and ask it to do stuff. And when it's done, I'm going to get rid of that agent because I don't need it anymore. These kinds of examples of kind of growing and contracting squads of agents is more like how we might consider a human force in much slower motion, of course. You expand a team, you contract a team when you don't necessarily need them anymore. Of course, that's sad, but for an agent framework, it's almost instantaneous. For more information, we'll wrap things up here with 5 minutes to spare. Wow. Most of the examples you saw today are taken not only from my GitHub, but from my book. So if you do want to check it out, I would really appreciate that. I really appreciate it. This is a lot of fun. Again, please reach out to me on LinkedIn, Twitter, or whatever it is. I'd love to hear what you thought about it with the session. And I hope the frameworks I've shown you and the frameworks we built and everything is going to help you go from A to Z. Because again, there's going to be tons of frameworks out there, but at the end of the day, you will know what's best for your agentic deployments. So good luck, everybody, and happy coding.